Well, as seen from the title, this unit is on work and energy and its conservation. We just got done talking about a conserved quantity, namely momentum. And now we have energy as well. So the big idea as we start out here is that energy is conserved and work and energy are scalars, as opposed to vectors like with momentum. And therefore, if you recall all the potential difficulty with dealing with the vectors with momentum, not that it's that difficult, but it certainly changes the considerations for how to handle the physical quantities. Work and energy is easy to deal with because we don't have to worry about direction. So, the types of energy. So for our purposes, we're going to consider kinetic, which has the symbol K, and potential, which has the symbol U. Kinetic energy is energy of motion, so anything that's moving has energy of motion, of course. And potential energy, instead, is energy associated with its position, waiting to act. It's a little bit crude and not too descriptive, but a little better definition would be energy that's a function of position. So now there's a strong connection between work and energy. And we start with F equals ma. And let's do a quick review from last unit where we have F equals ma. So if we multiply both sides by t, we get Ft is equal to mat. Now, I'm going to rewrite acceleration as delta v over t. So there it is, delta v over t times t. And so that's m delta v. So Ft is m delta v. Now, we know that m delta v is delta rho, change in momentum. Therefore, Ft equals change in momentum, which is impulse. And that connects all that together. So we've been down that road before, and it was a very scenic route, I might add. But the new stuff we want to think about is that, again, F equals ma, but this time, instead of multiplying it by t, I'm going to multiply it by d. And so Fd is equal to mad. Now, don't be upset. Okay. Now, recall from kinematics, with uniform acceleration, v squared is v0 squared plus 2ad. Do you see the ad in mad? Of course you do. So I'm going to solve for ad, v squared minus v0 squared over 2, and now say Fd is equal to m ad, which is v squared minus v0 squared over 2, and we have the following relationship, whereas before, with momentum, we have Ft is equal to j as impulse, Fd is equal to 1/2 mv squared minus 1/2 mv0 squared. Now for some definitions, we have work. By definition, force times distance. Force times distance. And kinetic energy, we define as 1/2 mv squared, both of which you've seen in the previous slide. And we just derived that Fd is 1/2 mv squared minus 1/2 mv0 squared. Since 1/2 mv squared is kinetic energy, then this would be the final kinetic energy, whereas this would be the initial kinetic energy. If you think of both of them simultaneously, you can get a nice figure 8. So that's delta K, change in kinetic energy. And so, we define the work energy theorem, extremely important for our purposes, that work net equals delta K, the net work. So delta K is this Fd. So expand it a little bit, a little more robust, consider that the net work, and we'll define that a little more carefully subsequently here momentarily. So in words, this says that the net work is change in kinetic energy. Very important, so I had to write it out for you. Units, joules, as you've probably already come across in previous experience. Newtons times meter is fundamentally what that is. Fd, force newtons, displacement meters. Okay, so 1 joule is 1 Newton meter. If you apply force over 1 meter, that's what we're talking about. So what it really means, this thing, the work energy theorem, is work sub total on object. So the total work done on an object is delta K. Does this remind you of the idea of the free body force diagrams? Namely, that the sum of the forces is ma. The sum of the forces acting on the object. Same idea here. Total work done on an object is delta K. Some examples, and I'll apologize because this is really better demonstrated, but I don't have the means to write at the moment. But if you're taking my class, you will either see it or have seen it. So, but you can imagine if I walk around with a book, okay, a book. I hold it in my hand and walk with uniform speed across the room. And the question is any work done on that book? Well, since there's no delta K, therefore there is no work done on the book. In other words, if you believe this at this point, I'm asking you to, or this, then the kinetic energy doesn't change. That's the giveaway, that no work has been done on the book, at least no net work. If I take that book and twirl it over my head or grab something else and spin it around in a circle, is there any work done on that object? Well, for the same reason, there's no delta K. Yes, the direction changes, but the speed doesn't. So no work done on the object if I spin it overhead. Even though it's accelerating and there's forces, there is no work being done. Now a cart, say pulling the cart at an angle, different angles, but that doesn't even matter at the moment. If you make the cart speed up, then you must have positive work being done. And if it's slowing down based on whatever you're doing to the cart, kinetic energy is going down, so negative work is being done. Now, this positive and negative is not in contradiction to what I said about work and energy not being vector quantities. Even though they're not vectors, there can be positive and negative work. Positive work increases kinetic energy. Negative work decreases kinetic energy. If I have a cart and it's on wheels and I'm pulling it with a string and then I put that string vertical while the cart is moving horizontal, perpendicular force, there will be no delta K from that either, so no work done on the cart from that force. At various angles, the car might speed up and slow down, and so plus or minus work will be done to the cart in those situations. So, when we consider the work done on an object, sometimes the kinetic energy changes, sometimes it doesn't. But what part of a force will change the K? If the K changes, it's going to be done by a force to change the speed, right? And that's not going to be perpendicular. It's going to be the parallel part. So here we have a block of mass M sitting on a table, an applied force F at an angle theta, and a displacement D. Well, the work done by that force, by a single force, is simply the part of the force that's in the direction of the displacement. So we have the parallel part. Oh, that's it. Same direction as the displacement. And we have the perpendicular part. That does nothing to change the kinetic energy of the block, and therefore it does no work. So it's F parallel times D, which is FD cosine of theta. And that angle is between the force and the displacement. The displacement is in this direction, the horizontal direction. All right, now that we got that squared away, work net equals F net times D, which is delta K. A little redundant perhaps, but I can hardly emphasize it too much. Let's consider a sliding block with friction. There's mass M. It's moving to the right by an applied force. And friction is saying, stop. But maybe it's not quite able to. Doesn't really matter in this case. There is a frictional force. From the applied force, the kinetic energy is going to do something. It's going to increase the speed. So the kinetic energy goes up from the applied force. That force does positive work. In like manner, from friction, the kinetic energy goes down, and therefore that force does negative work. Okay, that's about enough physics fun for this video. Remember, don't stand between a sow, grizzly, and her cubs.